In this example, we are going to use the second derivative to locate any extremas, which basically means we're going to take the first derivative, find critical numbers, and then take the second derivative, plug those critical numbers into the concavity, so into the second derivative. So if we do the derivative of this, first, before I do that, I'm going to rewrite this to make it a little more obvious of how I do this derivative. Because remember that sine squared really means sine x squared, right? So that's what I'm taking the derivative of. So if I do that, we're looking at, we have a chain rule going on, so we'll bring the 2 down. So 2 times sine x, and then that would become a power of 1, so that's just still there, times the derivative of the inside, so the derivative of the outside times the derivative of the inside. So the derivative of sine is cosine. All right, so there's our derivative. We would be taking that and setting it equal to 0. So sine x times cosine, 2 sine x times cosine x equaling 0. And we want to know when sine x equals 0 and when cosine x equals 0. All right, so for a sine x equaling 0, I think of it as the graph. Sine looks like that. So I'm going to get zeros at 0, pi, 2 pi, 0, pi, 2 pi, on and on and on with that pattern. And then cosine is at pi over 2 and 3 pi over 2. Pi over 2, 3 pi over 2. And then you'd have a 5 pi over 2. On and on. All right, so we have this repeating over and over and over and over again. Slopes of 0, slopes of 0. Those are our critical numbers. Critical numbers. All right, so we don't need to test all these different regions. What we can do is now take this and plug it into, or do the second derivative, and then we'll take that second derivative and plug in these critical numbers into it to see what kind of concavity we got going on. All right, so here's the tricky thing about trig, is that if I rewrite this right here, that our first derivative was 2 sine x cosine x, we could do the derivative of this, which would be a product rule, which is totally fine. And then we could take that product rule and plug in all these values. But this is the world of trig, is actually equivalent to something a little smaller. This 2 sine x cosine x is actually equivalent to sine. It's a double angle property, sine of 2x. So if I had a choice to do the derivative of that with the product rule, or the derivative of that, I'm going to do that one. So we'd get the same thing, but let me rewrite this as sine 2x. And so trig just has these kind of sneaky ways of rewriting things. And if I can rewrite them into smaller values, then I definitely will take advantage of that. So let's do our second derivative. If I do the derivative of this, this is going to be a chain rule. So the derivative of the outside is derivative of sine is cosine 2x, and then times the derivative of the outside. Sorry, derivative of the outside is cosine 2 times 2x times the derivative of the inside, which is 2. So our second derivative is 2 cosine 2x. All right, so next part of this is we're going to take our critical numbers. And so I have these values. There's probably going to be some sort of a pattern associated to it. So I kind of want to figure out what's the pattern we have going on. So let me plug in a 0, pi, 2 pi into our second derivative. So which means we're plugging it into this. So if I do cosine of 2 times 0, that's cosine of 0 times 2, and cosine of 0 is 1 times 2, we get a positive. Then if I do So a positive means concave up. So visually, we are going to have a minimum at 0, right? And then if I do pi, I'm going to take 2 times pi, so that's 2 pi. Cosine of 2 pi is here at 1. 1 times 2 is also 2 again. So that is also concave up, which means I have a minimum again. Let me just do one more, and I bet if I did this, plug in 2 pi, I bet we'll still get the exact same answer. So if I plug in 2 times 2 pi is 4 pi, which means we would just be another cycle through, sitting at the exact same high point of 1 times the 2 equals a 2. So it's also concave up because we have a positive concavity. And so we are still looking at a minimum. Then let's do the other values. So these are all going to be minimums, no matter which direction we go with it. And then here we have our pi over 2. So if I take second derivative, plug pi over 2 in, pi over 2 times 2 is going to be pi. Cosine of pi is here at a minimum. And so that's going to be a -1 times 2 is -2, which means concave down. So the shape would be this, meaning we have a max. So most likely, same kind of a pattern is we're going to have a bunch of maximums on this. So I'll go to 3 pi over 2. 3 pi over 2 is going to be 3 pi over 2 times 2 is 3 pi. So 3 pi would just be us back at that same bottom point. So that's going to be a -2, concave down. We're getting a maximum again. And then on and on and on. All right, so we have relative minimums, relative mins at plus, because we have this infinite amount of them, right? We can take these values and go in either direction. We need to generalize this. So plus or minus n pi, right? 0 pi, 1 pi, 2 pi, 3 pi. So in relative maxes at plus or minus, we'll take this, we'll go plus pi over 2 plus or minus n pi. Because we want to go, this thing repeats itself every pi. So we start at a pi over 2, and then we want to go a 1 pi, a 2 pi, a 3 pi further. So we have to have a starting value and then a pattern associated to it. But I need to add one last little thing, my n's. We need to define that where n is an integer. We can't have fractional values. We have to have integers on those. So that is our extrema. So with trig, things are a little bit more complicated. We have these substitutions that might exist. We have this pattern that's going to go on and on and on and on forever, unless you restrict your domain from like a 0 to a 2 pi, and then you limit yourself to how many answers you get. But if you don't limit yourself to how many answers, then you have to generalize it and talk about the infinite amount of them that you get.